for this class. So I realized that we should talk together about this class as opposed to other classes. I realized at least a couple of you that talked to me about what you want to do for a term project. It was oriented towards, say, material selection. I've heard quite a bit of that, and it's perfectly acceptable. As far as kind of the theory and the lecturing, material selection is a topic that's more for the fall class, which is 337-2. I have it on the screen here. The other side to that is in the fall, at least last fall, we asked the student to look into standards. We didn't give them really a material selection project. So that's why we have to be flexible and adjust essentially to what you guys want to do. There's definitely enough from what we've been lecturing to you to do material selection. And you can always pick it from any basic reference book if that's what you're interested in. I just want to kind of put the pieces of the puzzle together. So this term, the term project is relatively flexible. So you submitted your sheet, either life assessment, any kind of processing process, or material selection, which I've seen, and there's no problem with it. What happened last fall, again, is we asked for the project to be more specific to standards, because each industry has a set of standards, and it was really nice at the end of the semester to have everybody actually describe what they found for what they were more interested in. So if somebody says, oh, I'm going back to the Army, then they probably want to know about some of the military specification. Some people want to work in oil and gas, which seems to be popular these days. Then you go and learn a bit about API, for example. And we put it all together at the end of the semester so you can hear about what the others have learned as well. So it's a great class, and I guess I just want to make sure you understand that it's not a repeat between the fall and the spring. There are definitely some topics we have to cover each time, because not everybody is going to take both classes, and not everybody is going to take them in the same order. But there's a little bit of a difference. I would say that what we've done this semester is a little bit more on the theory, at least for my side. And I believe also for Professor Eager, he really went into the details of the forming. And in the fall, it's a little bit more general and more oriented towards meeting the expectation, if you will, in different industries. What do you have to do to get your product to the market? That's a little bit more the flavor of the fall class. Any question with respect to that? Because I did want to clarify. I didn't want. When I realized that I was going to start talking about factor of safety, I realized that it was kind of getting away from this class and talking more about standards and what it actually take to get into the market. So we're not going to go too far in that route this term. Okay, so that's it for that. If you were here yesterday, we talked about stress life approach. So that was the SN curve that we've been talking about for 2 classes now, where the higher the load, I should draw it one more time. We may use it actually. So the SN curve, you have the stress level, or the stress range, or the stress amplitude, and then you have the number of cycle or time, right? We've seen some creep curves that essentially follow the same type of behavior, and then we can have a curve that eventually going to go to a plateau or keep going down. That's when we talked about fatigue limit here. At a certain, it was 10 to the 7 cycles for practical application. For plastics, people use normally a lower number, but for metals, it's 10 to the 7. Now, this concept, I believe I mentioned, is used a lot. It's used in automotive industry. It's used some kind of oil and gas application when you know you're going to have fluctuations. It's also used for buildings when you have like wind loads and things like seismic load, things that are just going to vary. If you expect fatigue as being a problem, then you start wondering about what's your load level and do you have welds? And that's really what we're going to talk about today, or bolts. Yeah, right. Yesterday we saw that it was good to preload the bolts a lot, so you'll reduce the amplitude of the stress variation when you load them. And we talked about it after the class. I'm actually going to try to explain it a slightly different way. So if we think of the stress strain curve where we have the elastic portion and then we go into plasticity, and so that's yield here. If you preload the bolt, you may go, I told you about 80%. So you go up to right here. That is without anything happening. You just have your assembly. Yesterday we had this big bearing cranes, 4-6 feet diameter, with big bolts, and nothing is happening to it, and it's preloaded. So you wouldn't want to do that with plastics. We're really talking about metals, so we don't have any creep issue at 80% of the yield point. Now, what happens from this point when you apply the load is, I said it was about 7 times stiffer as an assembly because it's touching everywhere. So we had our little assembly here with a flange. So connecting to another side here. It also has a flange. So say I put, whoa. Yeah, we'll make it work. Now I need a top here. And I need a top there. So say I have those two pieces and I put a bolt here through them with a head. And what we talked about was a tension application. So we actually going to have something here that will lift this way, something that will lift it the other way. That's how the load is applied on those flanges, trying to separate the two pieces. What happens is if you have contact right here and you have contact right here and you keep it, it's a solid block that's exposed to your load variation in service. And because it's solid, it means that we're going to talk here about L as being the total distance between the exterior of the flange on each side. So that our delta L is going to be approximately 1/7 of what it would be if you applied the load directly on the bolt, because you have less metal. So with less metal, you'll stretch it more, and you have more stress and strain. Now, what that means here, because we're changing the magnitude of the strain for a given load, is we're going to go from 80% to say 90%. That's with the live load. So I will call it the dead load or the preload. Okay. If we didn't have it, if we did not have our contact here to make this a rigid block, just the bolt being pulled, then you'll start on another stress strain curve. So I'll make another one here. You start from 0, and it's 7 times this difference. So you go to 70% with the live load. Now, you can start seeing that as far as amplitude, it's very different. So you get a whole lot more amplitude of stress from loading and unloading when you don't have the preload. And that's why people have to torque boats up in critical application. It's not necessarily easy, because when I ask here for that 80% of yield strength, and a guy is there with a wrench, there are different ways to do it. You can ask for a specific torque. You can ask for a certain number of turns to load the bolt, but it's not super precise. So you do need, a good safety factor associated, but you're giving yourself a chance as opposed to having loose bolts, essentially. So that's kind of what we talked about, but maybe presented in a more summarized way. And referring back here to the amplitude, the change in amplitude for loaded, unloaded. So it's okay to stress the steel. That's what we do in forming application. You just compress it all the way, but moving it back and forth is another issue. That's where you start initiating cracks. That's kind of the idea here. The other concept was the Goodman diagram, and I don't think we have to restart it. It was this line where we go from, we look at the mean stress and the stress amplitude. If you're below the line, you're in the safe zone. If you're above, you're going to fail. And you have to draw one for different number of cycle to failure that you may consider. It's useful for bolts, because clearly they have a preload. So you can't go and take an experiment that was done going in tension compression and design based on that. You have to draw the diagram to get to the properties. All right. So today we're going to use. Any questions on the bolt issue? Today we'll use the same concept approach of talking in general, but for welds. You're probably aware there's a full module that's available to you, I believe on DVDs, on joining processes. It's hard to, I guess, talk to you too much about the welds without you understanding it a little bit. What I'm talking about is fusion welding. I mean, weld is a general term, so it could be soldering, for example, that you use for putting pipes together, plumbing pipes. But what we're talking about here is, in general, the most common way of welding structural material is arc welding. So you really apply a lot of voltage, you melt the metal between the two pieces, and you really form a weld. And there are more than a handful of processes, welding processes, that you can use depending on the application or the material. For aluminum, normally you need a shielding gas because it's so reactive that you can't just weld it with an electrode. So you need to bring the tank for pushing some gas over the melted metal. So if we take about a simple example, we have a T connection of any kind, and we want to put the two together. With bolts, that would be very difficult. I mean, if it's wood, you're going to put a screw through this and this side. If it's concrete, I don't know what you do. You put the rebar or something. But with metals, the easiest way is just say, oh, look, I'm going to come with a torch here. So I'll provide heat, a lot of heat. And my tip is also going to melt as I do it. So I provide extra material. And I'm going to melt the whole area here. So we call it the weld pool. So at some point in time, what the welder sees is this, is a final geometry. It's all red. It's very high temperature. And at the end of the day, this solidifies as weld bead. Now, we will see today that there's an area around the weld, and that never gets melted, but gets heated quite a bit and cooled down fast. And that one we'll call it the heat affected zone. For steels, if it's a good quality of a weldable steel, normally the heat affected zone will have a relatively good strength. If you're talking about aluminum, we talked about aluminum having all these precipitates to make it harder, right? So you quench it and then you age it. Well, it turns out if you heat it up again, you lose all of this. So you'll end up here in the heat affected zone sometime with a yield strength that's less than half what it is on the weld bead itself. Now, it's good and bad. You can think of it different ways because you reduce the yield strength. If you remember all our discussions about cracks, it means you're more ductile. So you can actually deform it more, if everything else being equal, without breaking it. Now, the downside, which we haven't talked a whole lot about, is for this type of fatigue here, stress life fatigue. Normally, the higher the yield strength, the more resistant you are, because you can essentially really just get the springs to deform back and forth. The closer you get to the yield strength, in this case maybe even just half the yield strength, you start having other things going on that are not reversible, so you're accumulating damage. So it's one of those properties here, probably I should have said it last class, but anyway, one of those properties that normally if you raise the yield strength, you'll raise that fatigue limit over there. Not always. I mean, it's just we're talking about trends here, so you have some idea of what to expect. You always want to verify. So that's the heat affected zone right here. And you can probably think of this, probably that's going to become intuitive to you, just even the way it's set up here. So this is melted at some point in time. This is hot, and this is cold. So when everything cools back down, you'll have distortion. There's just no question about it. If you restrain the pieces, so you keep, say, a 90 degrees between this one and this one, then you'll build up residual stresses. So it goes one way or the other. And it's definitely one of the main disadvantages of welding, that you have difficulties either controlling the residual stresses or controlling the distortion. But because it's so fast and easy to do, it's used a lot. It's worth learning about it and being careful designing for it, actually. So this is going to be most of today, but I did want to bring up a little bit of perspective on the class. We've been going for almost a month now, and we covered quite a few topics. If you remember, the title of the class says something about manufacturing and use. So I've put those up here with what we've gone through so far. We talked about applied loads through the example and geometry. I showed you about laser scanning yesterday. We definitely talked about aluminum and steel mostly. We could talk about others. I'll try to talk about some titanium project soon. And Professor Eager is going through forming, but as part of manufacturing, there's also heat treatment that we talked about a little bit, quenching and then heating up for aging, for example. We talked a little bit about annealing, which is to essentially soften the metal. And then the surface finish, I think you probably understand, forging has some advantages, but you have to control the anomalies. It's just really part of the whole sequence of going from a bulk piece of metal that you cast to a useful shape, a component. So you have many different ways of doing it. Professor Eager is going through a great deal of them. There are others, again, on the online modules or the DVD modules. Now, when you have that component, if your goal is to evaluate if it's good for service, for some application, and I didn't say that a whole lot, but for some application, you only need the basic properties. If the only thing that's going to happen to this table is once, I'm really going to jump on it. I only need to have a good safety factor for that load. It's only going to happen once. If I'm going to be, banging on it multiple times a day because this is in a warehouse where at UPS or something, then we're starting to talk about, bending lower weld. There's going to be some tension on the welds, and trying to see if this is going to break or not. So I do want to stress out probably the majority of the volume of metals we use. We don't really need a very sophisticated analysis to determine the design. But when we do have relatively critical application, and it's not rare either. I mean, when you think of something people will rely on for safety, for example, and there are a lot of them, that's where you need to be, I'll say, proactive in figuring out what's the worst case scenario that this piece is going to come out of the factory as. Is it with a crack, or just a very bad surface finish, or welds that are not done the right way? And then you start from those and figure out if they're going to have the life expectancy that you're looking for. And that's what we've talked about probably the past 3 or 4 classes when I started talking about fracture mechanics, and how we go with a component that has a crack in it. It could be a plastic, could be a metal. We talked about aircraft components. Pressure vessels are good examples where they have cracks. It's not rare they have cracks. We're actually going to talk about those next class with me next week. So how to make sure when they crack, it doesn't become a big deal. So it's a concept of leak before break that we're going to talk about, and how exactly we calculate for that. We did talk about fracture toughness. If you remember, that was our K1C. When you reach a critical load, then it snaps for a certain amount of a certain length of crack. So it's a combination of crack length and the applied load. Now the stress life, that was last time, and we talked about it quite a bit. So I would say so far, most of our real content, other than the examples, has been on fracture mechanics and the stress life approach. I'm not going to tell you how to go to a handbook and pick up a yield strength. You know how to do that. We did talk about the stress strain curve, if you remember, that the elongation at break is a useful tool, but it comes from that instability in the neck zone. So that was, I think, our contribution maybe to your general understanding of what you're going to do after you were able to make the shape that fits the function you want to have. Now you have to decide, is this strong enough, kind of deal. And again, it's basic properties. We have fracture mechanics, we have stress life, and there are others. And I could talk to you for days on corrosion, but if anybody is interested, we probably have to do it after the class, or maybe we'll do one time. But it's a big topic in itself. It's important, but for metals, I guess what I should tell you is, you're just looking for how much you lost. If you have a piece of metal on a ship, or you know, on a structure that's a pier or a bridge, you go for, after 20 years, you go for how much metal you have left. That metal didn't change. It's just that you lost a thickness, essentially. So you had to take off the rust and figure out how much. The way I explain to people, you have to look for the shiny metal, you know, and get the thickness of it. You know, with ultrasonic gauges, it's easy. You can do it from one side. It's not a big deal, but that's all you need to do. I mean, the interior of the metal doesn't get affected by corrosion. Plastics is different, right? I came to first class, I believe, with my ski bindings. I said that was a problem for me. And there wasn't any, you know, loss of thickness. I didn't use them in any harder way. I actually lost weight. So it had to do with degradation. And it's something that limits the life of a lot of plastics, how they're going to evolve over time. We think of them as good for environment because they don't have the red rust, you know, that steel will have, but they're susceptible to degradation by a reaction with the oxygen. And the polyethylenes, for example, they will have inhibitors put in to prevent that degradation. But then the question is, how much did the manufacturer put on inhibitors? Well, that's what tells you if it's going to be good for 25 years or 3 years or 7 years, maybe 10 years for my bindings. And I think it's important to know. So there were some projects I worked on where they didn't intend, you know, the pipe to be used with a water that had oxygen. So potable water's got oxygen in it, but if you have processed water, like any kind of heating system, the oxygen dies off because of the corrosion. And it becomes a big difference. If you want your pipe to work with potable water, you need a lot more inhibitors than you do for kind of a heating system. So it's, you know, people learn by mistake, but one of the purpose of this class is to sort of make you aware of some of the general lines that you want to avoid. It doesn't have to do with the creep curve anymore, right? We don't care. If it grows a little bit, if the pipe grows but doesn't break, that's fine. If it becomes brittle, like my bindings, that's a big deal. With PVC, it's the sun, so you get embrittlement by the sun. And therefore, you have to be careful if you're going to use some PVC pipes in exposed application. You know they will become brittle over time, and there are variations of PVCs that it will be more resistant, but you have to look for that if that's something that you're going to be building. So think of plastics as something that you have to be careful about high loads because it creeps. Doesn't mean don't use it for load application, but it's something, creep is really something to think about. And then the whole subject of degradation, which I sort of summarize for you here, but there's a lot to it in terms of making a plastic resistant to a specific environment for a specific period of time. You have to put in the right inhibitors, and a lot of them are proprietary actually for pipes. So you almost have to test them or trust the manufacturer that they're putting in the right thing, because they're not going to tell you all about it in general. Just the way it is. Fire resistance, I just want to mention the topic because, well, it comes more into play with large structures. On bridges, for example, if you decide you're going to go with a steel system for support under a tunnel, and you have to say, okay, well, what if there's a fire because of an accident in the tunnel? You know, I don't want the whole thing to fall down. World Trade Center is another example of, oh, shoot, we needed more resistance to eat of our main structure. But I say it in a general sense because in other applications, you just don't want things to cut and fire. In aircrafts, I cannot have any kind of plastic around the seats. It has to be a plastics that even if I put a lighter on it, it will kind of burn, but it will not ignite. And it's just part of the consideration for a design. You can't go with whatever plastic you like. It's got to be something that's going to burn, and they put the requirements sometimes, you know, harder and harder to meet. So people will put a composite particles into the plastics of these components to reduce the flammability, essentially. So and then that's bad for all the mechanics, but you know, it's the balance when you're doing a life assessment. You have to sort of balance everything out and say, okay, well, if that's what we're going to use, well, we're going to test that one. And if it's injection molded, for example, Professor Eager talked about that a little bit when he talked about the static mixers. Well, I have to take also that into account, all the orientation and what the particles are going to do to the orientation of those big molecules that we talked about. So there's just a whole lot that comes into any little change you may need to do to your material design. For wear comes into play in processing for the tooling, and Professor Eager talked about lubrication and all of that. I decided to show you that example just to, you know, open your mind to the idea that if you're going to go out and create this locking system for a cap on this flange here. So this is a flange to host a hose connector, and when there's no hose, then they put a safety cap on it, and the cap has this double cam shape here, so you see the groove. So you got two chances of not becoming loose completely. We started looking at this and ran a few tests, like you see here, and started getting all these super-sized chips. They're not staying all there here. So on the right image on top right here, you see these wear chips. This is bad. This is really bad. It's galling, that we call. So it's the removal of essentially pieces of metal, because it's in that case it was stainless steel and stainless steel. So two very similar material, which means a lot of friction between them. Similar hardness means a lot of friction and adhesion. So you chip out material. So we didn't run this test for long, and got those chips. It was done manually, maybe 10 times. So when you think of it, you can go and do your AutoCAD drawing or whatever software, SolidWorks, whatever you want to use to make a double cam. If you're going to wear it out in a couple of years of service, that's just not worth it. You need to think in a more clever way. In this case, you need materials with a sufficient difference in hardness that you'll avoid this. Now think of it, they're not always going to put a cap the same orientation. So if you move the cap around a little bit, you'll wear all around the flange, the piece that's underneath here. But these cams, they get worn out each time. So what you want to do is put the higher hardness on a piece that's the smallest. That's always going to be worn out. And they just didn't do that. It's not that hard to do. It's a small piece, right? And it's connected here. It's a different casting than the other casting. So that it's really an easy fix in this case, because you have an individual component that's small that you would want to go and make it harder, more resistance to wear, and you'll avoid the galling altogether. Or just decrease the clamping force is another option. Anyway, another example that I've been working on are elevator cables. You have a lot of redundancy on an elevator system, so it doesn't fall down. But it's all the same rope system. That there's redundancy in the rope system, but they're all the same essentially. So if you reach a critical condition where you start wearing one, chances are next time you're going to wear the one next to it and the wear next to it. And unless there's an easy way to find out, all of a sudden you're reducing your redundancy. And one of the design criteria is you want the rope to be much harder than all the sheaves that drive it. So if you wear the sheaves, it's not great, but nothing's going to fall. If you wear the cables, well, that's just not good. So it's a little bit of the same idea that you pick. It's different because it's more or less the same. The idea is sometimes you have to make a decision as to which one can wear, which one cannot wear. And that's just what I want to bring your attention to. So our joining, that's really the topic for today. I decided to start with a simple connection. This could be two pieces of pipe that you put together. So you have the pipe here, and then you have a flange, and then you have another one on top, and put bolts through it. It's a typical detail, and it brings a lot of issues that I wanted to introduce here. So we'll do it in a cross-section view here. So this is our cylinder that's in the bottom, and then we have a flange on top. And on the screen, I didn't put the bolt holes, but I will here. So you get some bolt holes to connect the flange I'm drawing to another flange that would be higher. Okay. It's a little bit the same way as here, where these are two pieces of metal. I think you realize now that we just can't cast everything. We'll do it sometime. We'll use ductile iron to make these as a single piece, the flange with the pipe. But it has a lot of limitations in terms of properties, and it's expensive to do. So the cheapest way is really normally to make a cylinder, make that flange, and then you want to weld them together. Now, I think we'll all realize, and I'll draw the next piece on top here. This is what we're connecting to. And we have our next section of pipe here. So this needs to resist tension or bending. And this is the tension spot. If you pull on this assembly, you'll see that it's going to try to open up in this corner. And it's too bad, because that's where our weld is. That's where we want to weld here on each side, because we have access. And by doing so, we introduce a little bit of a radius, which is good. So we're sort of smoothing out this sharp corner. Now, you could probably see that I'm melting it a little bit, this this piece here. So this is actually what's going to be melted on each side. Yep. And we have our heat affected zone. That'll probably go all the way through the thickness here. Where do you think it's going to crack?
At the edge of that weld.
Yep. With the weld, see, I did the weld bigger than the thickness of this pipe. It's a kind of it's not that hard to do it normally, but it doesn't help too much because what becomes your weak pat is right here through the toe. So you start cracking here and you go through the thickness here. So a lot of times for steel anyway, you're not really going to crack through the bead of metal. And that's an area where you have all the bending and everything. So it's a very weak point. The reason I bring that example up is it's the complete opposite to what you'd like to do with welds, because they have a reduced strength. So a lot of times, you know, what's going to govern the thickness of this pipe is or should be how much stress you're going to generate close to the flange. Not so much, you know, the internal pressure in that specific section, unless you are willing to go an extra step. And I thought we should do that one together. Maybe get a patent for it, because it's not used a whole lot, but the idea is not that complicated. So we still have our cylinder. And then we put a little sleeve on it for the last bit of it. Now, what it means, and this would be just a strap of steel. You probably won't. If it's big enough, you'll rather roll something around than try to come up with another cylinder. It depends. But you can easily weld the top here with a groove weld or an end weld. So you'll prep the surface like this, and then you put your bead in it. So that becomes welded. That becomes welded. Now, you end up doing the same weld that we talked about here. It's the same process. But now, when you put your flange over here, your highest stress zone has more material. So now when you put your bigger weld, you may have twice as much strength in that section at the minimum. Because not only you probably want to count only on the thickness of this, but in terms of stiffness, the stiffener also plays a role. So I'm using this as an example on how to move away the highest stress in the weld. So it used to be up here. Now we moved it down a little bit. We have much less bending load on that pipe, and we created essentially a stronger section up above. You could integrate this piece into this one, but then you have to worry about making that weld correctly to connect the two sections together. So this would be something. A lot of the ASME designs include things like that. They'll have ways of moving away the stresses in the weld. And one example actually be, I just thought of it, better. Say you want a cap, put a cap on a even if you have a little air compressor in a lab or someplace it's cylindrical, and then you need a cap at each end to make it a unit. One way would be to say, I'm putting a cap right here. And then you have to worry about, well, how am I going to weld this? Maybe I weld it, best case scenario, I weld it from the inside. It's not necessarily easy to do, but it's doable. Now, when I apply the pressure, this goes this way as a cylinder. This one wants to go up, this plate, the end plate, so you're stretching out those welds. A neat way that people do it is you come and have a dome type of shape near the end, and you put your welds up here. Now, the welds are there to hold the pieces together. They're not getting bent over anymore. I've seen this. I've actually had some of my clients coming up with ideas because it's a little bit more compact, but it doesn't make much sense. I mean, you can modify this one to a shape that would be a little straight section and then a bend. You guys know that it's not that hard to make such a shape now with sheet metal. So if you do it, now you have a stress riser. So there'll be some opening of the metal, but you put your weld over here. So this corner is all that steel that you rolled and you formed into shape. It's super strong. It's able to take some pressure variation. And you put your soft point away. If you lose, I don't know, 5% of the usable volume, I would say in most of the time that's pretty good. If you need to have it perfectly square, you have to design this so either it's got enough stiffener that it doesn't open up. That can be done. So if you put this plate thick enough and your cylinder here is also thick enough, but you can run into all sorts of issue, because if I make this super big, now the wall here is going to bow, because this is not going to deform. It's not going to expand in diameter, but the wall will. So I'll still open up those welds. So I guess we'll just say that sharp corners, we have to be careful with them with welds. It's nice to do because it's easy, right? If like the example we had there with the pipe and the flat flange, it's great. But for strength, it's a big issue. And that's what we're going to end up with for today, the strength and how to design with a weld. So by the time, say I decide, okay, this is the connection I'm going to do. I can go to a number of codes to help me out design this connection. So it will be done in a standard way. And if somebody ever asks me how I decided, the size of it, I'll say, well, I just used the code. So it's nice. Manufacturers of products like automotive, for example, have their own ways of doing it. So they do their own tests, they have their own procedures. They were not going to go by any of those standards, probably because they're too conservative. But we'll talk about this first standard here, which is used a lot, and we're looking at an SN curve. And this is not a joke. This is, if you're going to use structural steel, the AWS D1.1, which in principle is for structural steel. But it's used a lot, even for pipe design and other things, because it's prescriptive. It tells you exactly what to do, but it's super conservative. So it tells you if you're using a plain piece of steel, you have a stress allowable of about 20 up to 20 for the strain range. So put 22, 25 for stress range. That's a category A here. And then if you have these welds, like we talked about here, loaded and bending, it keeps going down to about 3 KSI. So it's very limiting. Okay, when we think about a material that we formed and it's 40 KSI strong or whatever we decide to make it, 50 KSI strong. Now we're talking very small stresses on those welds. Now this is really, it has all these safety factors built in, but you can see the difference between having and not having a weld if you're going to have a lot of cycles. But yeah, we say a lot of cycle because here we're already at 10 million. So if we go at 1 million, we're capable of taking 6 KSI. So think of a weld as a super taxation on your design if you will have cyclic loads. If this is again this chair that just a couple times somebody really gonna proof load test it, then sometimes you can get away without wondering about it. So vibration is a good example of situations where the welds will give up. So it happens on bridges. A lot of bridges, you have to design the welds in special ways. And we'll have to break here. We'll continue the discussion on welding on Wednesday. Monday, Tuesday, be Professor Eager talking about manufacturing, and then I'll do Wednesday and Thursday next week.